In this video, we're going to learn how to compute sample size when we're working with proportions and confidence intervals. So sometimes the scenario that you'll find is that in research, you don't have tons and tons of money to work with, but you have a fixed budget. And if you're paying participants to be in your study, you can't pay an infinite number of participants to be in your study, as great as that might be, because you'd run out of money. So you need to figure out a good number of participants so that you can keep within your budget. Another thing that researchers think about is margin of error. Suppose you want a specific margin of error. These formulas that we're going to use will determine the sample size so that you get that margin of error. Instead of just sampling until you feel like you have enough people and then dealing with that margin of error, you can start knowing a margin of error and then figure out your sample size to get that. So there's a relationship between margin of error and sample size. So here's the formula for margin of error. ME for margin of error. Some textbooks just use E instead of ME. When we're working with proportions, we take a Z star and then we multiply by our P hat times our Q hat, and then divide by N. So this should look pretty familiar because this is the last part, the part after the plus minus sign, from our confidence interval formula. This little piece here is just called margin of error. It's your little wiggle room that you add to your estimate. So the relationship here is that between n and your margin of error is that if n increases, so n increases, look where n is. N's on the denominator, so if you have a larger sample size, let's say 100, and you increase it to 1,000, you're dividing this top number, the numerator, by a larger number. Imagine taking a pizza and then instead of having 100 friends, you have 1,000 friends. Hardly anyone is going to get a slice of pizza because it's divided among so many people. So dividing by a larger n makes a smaller number. You take a square root, you multiply. Still, you're going to get a smaller margin of error. So as your n increases, your error is going to decrease. I'm going to write in here, or E. And that makes kind of sense because if you take a larger sample, it's like you can be a little bit more precise about what the population is going to look like. So you're going to have less wiggle because any sort of outliers that you have aren't going to have as much of an effect as if you had a sample of, let's say, 10. 100 people versus 10 people, you're going to move more towards the middle. So less variation, so less error. Now the opposite, if n decreases, n goes down. So instead of 100 people at the party splitting up the pizza, now you only have 10 people. Well, there's fewer people, so everyone gets more pizza. When you divide by a smaller number, this answer is going to go up, so your margin of error goes the opposite direction. E is going to increase. We have this inverse relationship because error and n are on opposite sides of the fraction bar. Notice that z and p hat and q hat, those are all on like the numerators. So if any one of those goes up, then margin of error will also go up. But n's on the denominator, so it has an inverse effect. So let's practice a couple problems. A researcher wishes to have a margin of error of 3% for their study. What's the sample size that is needed to get this margin of error at a 95% confidence level? So this is needed because you need to have a z-star value in your margin of error formula. When you're working with proportions, so 3%, don't use this answer as 3, use it as 0.03 throughout the calculations because see, p hat, it's a proportion. So there are two different scenarios we need to work with when we're trying to figure out the sample size. So that's our ultimate goal, figure out n. The two situations are that sometimes you have no idea what p hat is going to be. I'm going to write here p hat. If you have no idea what p hat is, then we use this like worst case scenario of, well, I have no idea what p hat is. Is it going to be large? Is it going to be small? So we pick like an average. So we pick p hat to be the middle, average middle. pick it to be 0.5. So 0.5 is like that worst case scenario. It's right between 0 and 1. So this is kind of a guess. Sometimes some textbooks would say p hat sub g for guess. All right, so let's calculate this margin of error. ME is equal to, let's write out the formula, z star, and then big square root p hat times q hat divided by n. Let's fill in what we know. 95% confidence level. We've worked with this a lot by now, so 1.96 is the z star value. It's the critical value. And then multiply that by p hat. Well, we guessed it was going to be 0.5 because we had no idea what the sample proportion might be. Q hat is the complement, so that's also 0.5. And then divide by n. Oh, and well, we know what our margin of error is. It's 0.03. So if we look at our margin of error formula here, notice that n is on the denominator. This is what we want to solve for. So we could go through quite a bit of math, and let's go ahead and do that. And we're going to solve for n, because really this is a margin of error. We were told what we needed it to be. We needed to find n. So we're going to do some algebra and we're going to solve for n. So let's start by, well, we need to isolate n. So what do we need to get rid of? Let's start by getting rid of 1.96. So we're going to divide by 1.96. Divide by 1.96. All right, so those are going to cancel out. I'm going to leave this as non-simplified for a reason, so just bear with the algebra. 0.03 divided by 1.96 equals 0.5 times 0.5 divided by n. And really, this is the only time you actually have to go through all of this math. In the end, I'm going to show you the shortcut formula, but I want you to understand where this came from. Okay, so I'm still trying to solve for n. I notice that I have a square root here, so I'm going to square the entire quantity to get rid of that square root. That means I'm also going to square the other side. So I get 0.03 divided by 1.96 quantity squared equals 0.5 times 0.5 divided by n. All right, so we're almost there. We're still trying to get n all by itself. Give myself some more space here. All right, so we want n by itself. Let's go ahead and multiply both sides by n. It gets it out of the denominator and puts it onto the numerator. So cancel, cancel, n times 0.03 divided by 1.96 squared equals the 0.5 times the 0.5. All right, we're almost there. We want to get n all by itself. We need to get rid of this coefficient, these numbers right here. So the way I'm going to look at this is I'm going to multiply by the reciprocal, because the fractions, if I reverse them, flip them, then I'll get some numerators to cancel, some denominators to cancel. So I'd end up multiplying by, I'm going to squeeze this in here, 1.96 squared over 0.03 squared. Let's make that equal sign a little bit more obvious. And go back, 1.96 squared over 0.03 squared. So what happens is you get the 03 squareds canceling, 1.96, 1.96. So the squared, I multiplied it, right? Applied it to both the numerator and denominator. Think back to your exponent rules. All right, so here we are at the end. N equals 1.96 squared divided by 0.03 squared times 0.5 times 0.5. So remember what all these numbers stood for. We had n, and 1.96 was our z star value. Let's change colors here. Let's go we had a z star, that was the 1.96, and that number is squared, as well as the 0.03, that was our error. And then what was 0.5 and 0.5? Well, that was our p hat and our q hat. So I just went back and replaced those symbols, replaced those numbers with the symbols. So all of this right here is your sample size determination formula. It's just a bunch of algebra that's based on the margin of error formula. So this is what you'll use to determine sample size. Now I went through and algebraically showed this. You don't do that every time, just go straight to the formula. Well, now that we've solved for n, let's go ahead and do some math. 1.96 squared divided by 0.03 that is squared. Make sure to use good order of operations here. Then multiply by 0.5 and then multiply again by 0.5. And I get 1067.1 that is repeating. So this 0.1 that's repeating, let's go ahead and write it out differently. 0.11111 goes on forever. You're not going to be able to sample 1/9 of a person, so go ahead and round up. Instead of taking a part of a person, just take the whole person. So round this up to 1067. Oh, I lied there. 1068. Even though 0.111 in your elementary school rounding rules, you'd round down, in statistics we have funny rounding rules. We want to round up because we'd rather have a few more people than too few of people. So whatever your decimal place is, just round it up. Some textbooks say round however you want, it doesn't matter because, heck, 0.5 was a guesstimate anyways. Who says that 0.5 was right? So it's all an estimate. I tend to round up. Just read the directions generally. All right, so it takes just a little over 1,000 people to get a margin of error of 3% at 95% confidence. So let's look at our second option. This is if we had done some sort of pre-study, or maybe someone had done other research, or maybe you just happen to know what p hat might be. So maybe you happen to know that p hat is not 0.5, but it's closer to 0.07. Let's go back to our sample size formula. N equals z star divided by e squared multiplied by p hat multiplied by q hat. All that's multiplied together. If we happen to know what p hat is, then we'll go ahead and plug that in instead of using the 0.5 as before. So n equals, we're going to use the same facts as before, 1.96, keep the same margin of error, 0.03, quantity square, and then p hat times q hat, so that's 0.07. So q hat would be the complement, 0.93. So just subtract 0.07 from 1. So now I'll go through and do some math. 1.96 divided by 0.03, and then I'm going to square this on the calculator. Then I'm going to multiply that answer by 0.07, and then multiply that answer by 0.93. And I got a wrong answer. Let's try this again. There we go. All right, I got n is equal to 277.9. Now remember, we can't sample a fraction of a person, so I'm just going to go ahead and round this up to 278 people. So there would be 278 participants in our study. So what's different about this? Before, when we had no value for p hat and we went with basically the largest possible, it took over 1,000 people to get a margin of error of 3%, 0.03. But if you do have an idea of p hat, like someone else's research, you've done preliminary research. If you know what p-hat might be, you'll get a smaller sample because your proportion is like a little bit more accurate to start with. So it takes fewer people to get that desired 0.03 margin of error. If you're paying someone $100 to be in your research, paying 1,000 people is a lot more expensive than just paying almost 300 people to be in your research. So when you are figuring out sample size, there's kind of two options, and you just have to read problems carefully to figure out, do they give you some sort of proportion to start with, or is it free for all, you have no idea, so you'd use 0.5 instead. Just read each problem carefully.